Everyone, and welcome to TLE Eliminators video solutions for the CP-31 sheet. Today we'll be discussing the 1600 rated problem, Chocolate Bunny. So let's pull up the CP-31 sheet and open up this problem. Okay, so first off, it's an interactive problem. So that just means that we need to flush the output and we should not use fast IO, right? So we need to keep that in mind. We feed you a permutation P of length n consisting of the elements 1 to n. So there's a hidden permutation of length n. We can do the following guess. Give us two different indices I and j, and we'll reply with pi mod pj. Okay, so the remainder of pi by pj. We have enough patience to answer at most 2 times n queries, so you should fit into this constraint. Can you do it? As a reminder, a permutation of length n is an array consisting of n integers from 1 to n in an arbitrary order, right? So a permutation can be in any order, all the integers from 1 to n. Input is simply a single integer n, and then the interaction is like question mark xy, and then we get an output of whether what is the value of px mod py. When we finally guess the permutation, we have to print this new line bang character and then print the array p, right? We need to print the permutation. So we need to discover the whole permutation by asking these types of queries like what is this mod this, what is that mod that, right? So that's basically the question, and goes up to 10 power 4. So roughly big O of n log n type of constraints we see. Remember, it's an interactive problem. So because the input output and flushing takes a while, so this is about big O of n log n constraints itself. Okay. So let's get on with the problem. Let's just write the expected time complexity to start off. So expected time complexity will be big O of n log n ish, big O of n, possibly big O of n squared if your input output is fast, but it depends from language to language, right? So expected will probably be one of these two. Okay, so let's get into the ideas. Okay, so ideas. What does the problem tell us, right? So we have a hidden permutation and we know nothing about this permutation, right? We don't know what the elements are. We just know that the elements will be all the elements from 1 to n, correct? So like 1 2 3 4 5 6 7 8, and they're distributed in some random way. What we're getting is we are allowed to do 2n queries, right? Max 2n queries. And what is the information we're getting from a query? We take two elements, let's say this is element x and this is element number y, and then what we get is we get px mod py. Okay, and we need to think about what kind of information are we getting from px mod py. All right, so how can we tease out the elements of the array, what the values of the array are, using only px mod py? So let's give px and py some values, so you know we have a feel for what's going on. So let's say px is equal to 3 and py is equal to, let's say, 5. Okay, so then what does 3 mod 5 give us? All right, so let's check 3 mod 5. Okay, and 3 mod 5 will simply be equal to 3 itself, right? So we get that px mod py is equal to px only in this case. In what case? If px is less than py, then px mod py is equal to px itself, right? So this does give us a nice idea, like, okay, see, we're doing px mod py and we're getting one of the elements itself. So maybe this is the way we're going to figure out how the elements are arranged. Okay, so we'll think more on this, right? We'll think more on this and we'll see what if it was the other way. Okay, what if it was the other way? What if we got py mod px? What if we got py mod px, right? And then in that case we would get 5 mod 3, right, which is equal to 2. Now the issue with 5 mod 3 is we don't have any information coming from this 2, okay, because not only is 5 mod 3 2, right, even 8 mod 3 is also 2, correct? So we don't know whether it is 5 or 8 or 11, all of these numbers it can possibly be. So we have no idea which one of these two are. So this operation does not seem to be much useful. But one thing we can tell, one very clever observation is there, that, okay, so this was the first observation, that if let me just write it as observation 1. Okay, so the first observation was that if px is less than py, then px mod py will be equal to px itself. Okay, and now the second observation is when we have py mod px. Okay, py mod px, assume here that py is greater than px. Okay, we're just assuming that py is greater than px, and we have py mod px. What happens? Well, we know that the mod value, like for example, if we have x mod 3, right, x mod 3 will always be less than 3. It will be equal to 0, 1 or 2, right, the remainder which is given by 3. So every number mod some modulo value will always be less than m, right? It will be between 0 and m. So we get that py mod px is going to be less than px, right? We get that py mod px will be less than px given that py is greater than px. Okay, so let's write down our observations. So our first observation was going to be, let's write them down neatly. Okay, observation 1. So assume py is greater than px. Okay, then px mod py is equal to px and py mod px is less than px. Okay, and this is a very interesting statement, these two things in conjunction. If we take these two observations in conjunction and maybe try pause the video and try to figure out how we can proceed from these two statements. Okay, so the very interesting thing which happens when we take both these two statements is that when you take 5 mod 3 and 3 mod 5, okay, and you take the maximum value of both of them, right, you will get 3. Okay, and the reason is that, see, one of them is equal to exactly px, the smaller one, and one of them is equal to less than px, right? So the max of these two will always be px itself, right? So max of px mod py, px mod py and py mod px will be equal to px. Okay, it will be equal to the smaller one, px less than py. Okay, so it will be equal to the smaller one, and this is the main observation which is going to help us, that whichever one is giving us this smaller one, that if we take max of them, that's going to give us the smaller one of the two, right? So basically, let's note this down like this: given two positions x and y, we can figure out the smaller one of px and py in two queries. Okay, so not only can we figure out its value, we can also figure out its position, and that's also simple because we know that px mod py is equal to px, right? So when we do x comma y, if that gives us px, then that means that the smaller one is going to be here, right? The smaller one is going to be at x. But if we do y comma x and that gives us px, then we know that the smaller one is going to be at y, right? So we know the position of the smaller one also, right? So this is giving us a lot of information. It's going to give us that which one is the smaller one and also position of the smaller one, position of px as well, right? So it gave us the value of px and the position of px as well. So which is the smaller one and where it is located, whether it's x or y, correct? So these are the two things we're getting from two queries. This will require two queries. Okay, so this gives us an idea. See, we have 2n queries, right? We have 2n queries. So if each query is giving us a new element, then that way we can figure out all the elements, right? So we have 2n queries available, right? So what we'll do is pick two numbers, okay, x and y, compare px py, right? Compare px py, find the smaller one, right? Find the smaller one, and update that array. So now we know the smaller one, right? So we can store it in our local array. So update the array, right? And whichever was larger, we'll use in our next step. Okay, we can use in our next step. We can use in the next step, right? And that's basically going to be our idea. Like pick two numbers x and y, whichever is the smaller one, update the array and use this a larger one in the next step. right? Like, so let's say py was larger, so next time we'll use py and pz, and then again which one is larger we'll use in pz and pw, and so on, that kind of way, right? So in the end, using 2n minus 2 queries, we will find all the elements except the largest one, right? All the elements except the largest one, because obviously the largest one is not smaller than anything. So we'll find all the other elements, right? Because we're using each element, and whichever is larger, we're going with that. So the smaller one gets placed. We'll find all the elements except the largest one, and their positions also, right? So we'll find the whole permutation except for the largest one, and that one we can just add manually, right? So that one we can insert ourselves. Right? Because that's the only one remaining. So that's about it. Always just choose two px and py. Initially we can just choose px, py randomly or whatever, and then we can ask and compare, and then we can repeat this step, right? And that's about it. There are many ways to implement it. You can implement it with a loop, with some temporary variables, etc, etc. The way I did it was a bit more generalized. I did it with like a stack. All right, so what I did was I did a stack, basically use a stack data structure. Okay, stack data structure, and all the elements are there. Okay, all the positions are there, p1, p3, p4, p5, p6, so on, right? And what I'll do is I'll take the top two elements of the stack. Okay, so this will be my px, this will be my py, right? Now whichever is smaller, I find that and I put it in its correct position in my answer, right? I find that using my two queries and I put it in my answer, and the other one I return to the stack. So let's say p5 was larger, so p6's value I found, and now p5 value I still need to find, so I'll put it back on my stack, right? So now my stack will look like this. So when I repeat the process, I get everything's value until like one element remains in the stack at the end. That element obviously has to be the largest one, right? So that's my approach to implementing it. You can implement it in your way. Any decent way of implementing will have a time complexity at most big O of n, right? Big O of n. Even big O of n log n will perfectly pass. Memory complexity for this approach is also big O of n. All right, so pretty straightforward question actually. Just need to know some modulo properties, so some very basic number theory, and you need to be like, if you're new to interactive problems, sometimes interactive problems will just feel scary, right? So you need to overcome that. So that's why this problem is there. So you can understand that interactive problems are pretty straightforward usually. You just need to, think logically, think with a clear head how it's going to be done. Okay, so let's have a look at the code. Right, here's the code for the problem. So here in my code, I use two things. I use a stack for the which positions are left, and a set for which values I need to still fill, right? So why do I have a set for values? Because in the end, whichever value is left over, I want to put that in my end value. So that's why I have that. Anyways, you can obviously implement this in a better way. But yeah, this implementation is also decent using the stack approach. So as long as the stack size is greater than equal to 2, I take my top two elements, I call them x and y. I will query x with y and y with x. Okay, x with y and y with x. I'm going to query both of them. Whichever value I got, obviously I'll erase that one. And what I'm going to do is basically, if the first one is greater than the second one, that means that the first position is this smaller element a1, and I put that there, and I remove this position. I remove the x position, so I need to push back the y position since the y position is the larger one, right? Now, if the second one was larger, then that one gets this value, and I push back the x position since that remains on the stack. So that's it. While this loop continues, it's going to find all the elements except the last one. And finally, the last element I can just put manually, and then I can output the whole thing, right? So pretty straightforward, interactive. And the 2n query bound is also very generous, right? So there is like a pretty direct answer, I would say, right? That's about it for this question. Thank you for watching. If you had any doubts, do rewatch the video, do a dry run based on the idea I gave you, based on the code, right? You'll understand it pretty quickly. All right, thank you for watching, and see you in the next solution. Bye bye.